In this module, we're going to start this entire series on language modeling. Okay, so far we've looked at acoustic models, specifically HMM-based acoustic models. We've looked at how to use WFSTs to represent the entire ASR pipeline. And now in the next two or three lectures, we're going to dive deeper into how language models are implemented. Okay, so the language model, just to remind you, is the very final component in the ASR pipeline via which you reorder word sequences, right? So that you end up with the word sequence which is most likely in your particular language. So language models, like I just mentioned, it provides information about the word reordering, that she taught a class is a much more likely sequence of words than she class taught her. So the grammatical constraints which hold over a language are captured by language models. You can also think of a language model as providing information about the most likely next word. Okay, so if you had the context she taught a, then the probability of seeing the word class is much more likely than the probability of seeing a word speech, right? So language models are also typically defined in terms of the probabilities that they assign to the next word prediction given a word history. Okay, and language models, what is the role they play in speech recognition? Beyond just kind of ordering of words, which are most likely in the specific language that you're recognizing, another important role of language models for speech recognition is that you can have exactly the same phone sequence, which can be rendered as two different word sequences. Okay, so there is this inherent ambiguity in that the phone sequence can be recognized as distinct word sequences which are entirely different. So for example, she taught a class could be sheet or tuck class. So here, just by kind of moving around the word boundaries, you have exactly the same phoneme sequence, which is rendered as these two completely different word sequences. And here, a language model can come in and say that the first word sequence, which is she taught a class, is much more likely than she taught a class. Okay, and so then that's how the language model kind of disambiguates, which could be a more likely word sequence. Language models are also widely used in applications beyond ASR. So machine translation is another famous example of where language models come into play. Handwriting recognition. So if you're trying to write a sequence of characters, and you're trying to recognize what this person's handwriting is, then having a character-based language model could be useful. Okay, because you know that a certain, even though the squiggles look like it is some particular character, because of the language model bias, you know that there are certain characters given the context which are much more likely. And so this is useful also in handwriting recognition or even OCR, right? Optical character recognition. Spelling correction of sentences. So when you have spelling correctors, like when you're typing out your queries on search engine, if you misspell the word, then it can it'll suggest the corrections of your particular words, right? The fixed kind of queries. So on Google, if you misspell a word, it'll show you search results for after having corrected for those misspellings, right? So here the spelling correction system is at work. And here also a language model could be useful because the corrected spelling appears within the context of certain search queries very often. And so if you misspell it, it knows that, I mean, this is the most likely word, the correct spelling of a particular word. And then there are endless, okay, applications of language models. So summarization, any kind of natural language generation model, so generating dialogues, and also kind of information retrieval applications, all of these utilize language models. Okay, so this is a very useful kind of tool. So we will go through techniques which are more broadly applicable, and they're also applicable in the context of ASR. I just want to briefly list certain language modeling toolkits which are widely used. So SRILM is out of SRI, and this is in fact the toolkit that you'll be using in your first assignment. KenLM is another toolkit which works very well and efficiently with large language models. And then there's also a third library called the OpenGram Ngram library, which borrows notation from the OpenFST libraries. Okay. All right. So now let's um, get started on defining language models a little more formally. So what is a statistical language model or a probabilistic language model? So one way to think of it is that if you're given a word sequence W, what is the probability of W, right? So what is the prior on W? So you can write W as, you can decompose probability of W using just your product rule. So the chain rule. So this is, here is the decomposition, right? Which all of you recognize. Now, immediately when you look at this decomposition, what is the challenge? Okay, so you see that you start with just probability of W1 followed by probability of W2 given W1, W3 given W2, and then slowly you end up with these factors which are looking at the probability of word given very long contexts, right? And when you have these long word contexts, then immediately you're going to run into a sparsity problem, which is how do I estimate these probabilities? So I'm looking for the word denoted by Wn in the context of the word sequence W1 to Wn minus 1. Okay, so how would I go about estimating such probabilities, especially when I have long word contexts? So what would be kind of the simplest way in which you could think about estimating word probabilities? Just accumulate counts, right? So just um, compute these relative counts, and these relative counts will serve as your word probabilities. So how would you do that? If you wanted to compute something like the probability of W2 given W1, then I'm just going to accumulate counts of how often the sequence W1, W2 appears in a large corpus of text. Okay, and then once I have this, I can just suitably normalize this count to get my probability of W2 given W1. Okay, so here's an example. So I want to find the probability of class sheet order, which this is an example which appeared in an earlier slide. Then this would involve the following computations, which is counts for sheet order class appearing together, right, divided by the total counts of sheet dot which is the word history, right, for class. So this is the normalized counts corresponding to class given sheet order. And this would be your probability. This would be your estimate of predicting the word class given the word history sheet order. Okay, and these counts you would just derive from a very large corpus of text in English, which is easily available, right? And actually, for many of a large fraction of the world's languages, you can assume access to large text corpora. And so you just need to skim through them and then accumulate all these different counts, and then you have your desired probabilities. So, what's the catch here? The catch is that you're never going to see enough data. Okay, even for something which only involves 3 words in its history, you're inevitably going to end up with a trigram which never appears in your text corpus. Okay, and this is not a cooked up problem. You can go to very large repositories of ngrams, and you can search for what you think is a fairly reasonable trigram, and you'll see that there are no counts of those trigrams in that text corpus. Okay, so this problem only gets worse as the size of your word history increases, right? So that's the sparsity problem that we mentioned. So as you're kind of conditioning on longer contexts, you're inevitably going to run into this issue of never having seen these contexts in your text corpus. Okay, never having seen this combination of words appear in your text corpus. All right, so how do we get around this? So here we can make a simplifying Markov assumption. Okay, so we'll say that I don't actually care about the entire history of words to predict the next word, but I'm only going to look at a fixed memory of previous words and then make my prediction about the next word. So I'm going to forget, things which I said way back. I'm only going to look at the previous, say, M words. So this gives us what are known as Ngram models. Okay, and here N denotes the order of your your Markov model. So one first order language model, also referred to as a bigram model, means that I'm only going to consider the previous word to predict my next word. Okay, so here you can see that W2 given W1, that factor stays intact, but according to your product rule, this should have been W3 given W1 comma W2. But now I'm saying, forget it. I'm only going to look at the previous word, which is W2. I'm going to forget W1. Okay, and you keep doing this. So you're making this fairly strict assumption that the probability of the next word only depends on the probability of the previous words. You can imagine loosening this assumption a little bit. Okay, so increasing the order to say a second order language model, also commonly referred to as a trigram model. So in a trigram model, you're not looking just at the previous word, but you're looking at the previous two words. Okay, and then so similarly, you can have the third order language models. So they're also referred to as four-gram models. So an n-gram model is an n minus one order Markov model. Okay, so that's the simplifying assumption that you're going to make. And turns out this assumption, even though at the face of it seems fairly naive, it works reasonably well. Okay, it does a reasonable job of giving you the kind of reasonable probabilities of entire sentences that appear in your corpus. Okay, so what would your n-gram probabilities look like? So for the unigram model, the probability of a single word would just be the count of that word having appeared divided by the counts of all the unigrams in your text corpus. And in a bigram model, if you want to find the probability of W2 given W1, you want to look at the counts of W1, W2 having appeared together in a large text corpus divided by the count of W1, right? Which is the same as saying it's the count of the sum over all I count of W1 with Wi. So this means you want to look at all the co-occurrences of words with W1 as its previous word. You sum over all those counts. So you get the total count of how many times W1 appears, and then that is your normalizing factor in the denominator, and then you get probability of W2 given W1. So it turns out this count-based estimation is actually the maximum likelihood estimate, right, of these particular probabilities. All right, so here's a very simple example, just so that you get a feel for how to use these bigram probabilities to compute the probability of an entire sentence. So assume your text corpus only contains these three sentences. Okay, and now I'm going to construct a new test sentence. I'm going to ask you what is the probability the cat chased a mouse using a bigram model. Okay, so since you know that you're going to use a bigram model, you can decompose this particular probability into the product of these bigram probabilities. Okay, the given, so here this denotes the start of the sentence, and this marker denotes the end of the sentence. You will see this in your SRLM models that you build for assignment 1 as well. So a probability of the given start sentence, probability of times probability of cat given the, and so on. And then you have the sequence of probabilities, and now you're just estimating each of these. Okay, so the given start, you can see that the was the starting word in every sentence, and so that's in your numerator, that count, divided by the number of times that you have actually seen the word the, right? Sorry, you've seen the start of sentence marker. So that would be 3 in the denominator, and so that's the probability is 1. Similarly, let's look at, so say probability of a given chased. So chased a, how many times does chased a appear in this particular corpus? Just once, right? And then you want to divide by the probability of chased. So that's how many times does that appear? um, just twice, right? So the denominator is 2, the numerator is 1, so you have half. So that's it. This is the probability of the sentence, the cat chased a mouse using a bigram model. All right, how about the following sentence? The dog eats cheese. How do I estimate the probability of this sentence using a bigram model? So I do the same thing, except when I consider this bigram, which is dog eats, right? And if I query my text corpus, I don't see dog eats anywhere, right? I don't see this bigram appear anywhere, which means the numerator is 0, because there's 0 counts of this bigram. And so immediately this reduces the probability of this test sentence to 0, okay, because I encounter this unseen Ngram situation. So this is due to unseen bigrams. And this is something, like I mentioned earlier, you're going to encounter very frequently, right? Especially when you're dealing with, say, higher order Ngram models. So how do we deal with these unseen Ngrams? And this we're going to come back to. In fact, the next lecture is going to be almost entirely dedicated to this particular countering this particular situation. Okay, so the end of this lecture, we will slightly set the stage for how we go about dealing with unseen Ngrams, and then we'll tackle this in much more detail in the next lecture. Okay, so I want to make one distinction between what we call open and closed vocabulary tasks. So if you're working with what is called a closed vocabulary task, the assumption is that you have a fixed vocabulary, okay, and that you know all the words in advance. But the more realistic setting is that you don't know the words in advance. Okay, so this is what is referred to as the open vocabulary task, and that you're bound to encounter out of vocabulary words during the test time. So OV is short for out of vocabulary words. So the solution is in for language models is that you create a particular marker which signifies an unknown word, which means now you need to estimate unknown probabilities, right? Um, Here is one very naive way in which you can do that. How do you estimate these unknown probabilities? You do actually fix a vocabulary V. Okay, you determine it by, say, looking at what are the most frequent words that could appear in this particular language. Look at your training data, change all the words in the training data which are not in V to Ankh, okay, and then you train its probabilities just like you would for a regular word. And now at test time, you use these Ankh probabilities for words which do not appear in your training data. Okay, this scheme has lots of issues. So here you're just clubbing together all these unknown out of vocabulary words as Ankh, right? And estimating its probabilities during training by just changing all the words in your training data that do not adhere to some vocabulary V to Ankh, and then using those probabilities at test time as your Ankh probabilities. Which is so clubbing all the unknown words as this one Ankh is kind of very suboptimal. Okay, but this is just, I just want to introduce this notion of an unknown word, okay, so that you can assign this label to out of vocabulary words during test time. Okay, now how do I evaluate a language model? So now I've built this language model which gives me the probability of predicting a particular word given a word history. How do I evaluate one language model from another? Okay. So there are two forms of, you can think of two forms of evaluation. There's an extrinsic evaluation, which is that you don't evaluate language models in a standalone manner, but you incorporate language models within a larger system, okay, and then you evaluate that system, use the evaluation metric of that system. So for example, in speech, what would that mean? If I wanted to compare two Ngram models A and B, I'll use both within a specific speech recognition system, and I'm going to fix every other component so that the only thing that is changing in the entire pipeline is the language model. And now you compare word error rates when you used Ngram model A and you used Ngram model B, which is the evaluation metric for the speech recognition system. Okay, so this is the extrinsic evaluation of the language models. But as you might have kind of thought about it, this is very expensive, right? Now, each time I want to compare two language models, I have to run through an entire decoding of the ASR system just to see how the language models are doing. So there's also an intrinsic evaluation for language models. where you're going to evaluate it in a standalone manner. Okay, so there are two ways. So there's a very popular metric which is known as perplexity. So I'll motivate perplexity by trying to answer the following two questions. The first question is, how likely does a language model consider the text in a test set? Okay, so I'm given a test set, and I want to see how likely does my language model think the text in the test set is. Okay, so this is, if I can answer this question reasonably, then that is a good metric. And the second question that I'd hope that my intrinsic evaluation measure will answer is, how closely does my language model approximate the actual test set distribution? Okay, and it turns out perplexity, which is the most common intrinsic evaluation measure for language models, perplexity can be used to address both these questions. Okay, so let's look at them one at a time. So here's the first question. How likely does the model consider the text in a test set? So you can think of the perplexity of a test set as being the so it's inversely proportional to the probability assigned to the text in my test set by my model. Okay, which means that the larger the probabilities that are assigned, the smaller my perplexity values are going to be. So you can equate perplexity to some kind of a surprisal measure. Okay, meaning how surprised am I to see this text in my test set? Okay, if my model is really good, then I'm not going to be very surprised. If my model is bad, which means that it's not able to deal with the text in the test set well, then my surprisal values are going to increase, right? I'm going to be very surprised to see the sentences in the test set. So here is one way in which perplexity can be defined, just the reciprocal of the probability assigned to this text by my model. There's one small modification to finally arrive at my perplexity measure, which is that I also need to normalize it by the text length. Okay, so here you can see it's the reciprocal of the geometric mean of the text in the test set probabilities, right? So here n is the number of tokens in my test set. Why is this? Why should I normalize by this root n? Okay, so think of the following setting. You consider a sequence of n words, okay, where each word at each position, you're going to choose IID from a dictionary of size L. Okay, then for any test set, according to my measure of perplexity, which is this, what would the perplexity evaluate to? It would be 1 by L to the power n, because recall, I have the sequence of n words. Okay, and I'm saying that each word is chosen IID from a list of 1 to L words. Okay, so and I'm going to choose this uniformly at random. So one of these words I can pick. So then what is the probability of this particular sequence of n words? It would just be 1 by L to the power n. Okay, and then if I take so if I normalize with this 1 by n, then I end up with L, right? So the perplexity becomes L. And that is exactly what I want. Because what is this saying? That at a particular position in this particular sequence of words, what is think of like kind of how many words can I kind of distill the next word to come from? Okay, so let me say that again. What the perplexity of L means is that if I'm at a particular position in a word sequence, I want to look at how many, what is the number of words, next words that are most likely. Okay, so here that number is L. It's just the entire dictionary size because I can't do any better, right? Because I'm just picking, my model is just picking the words with uniform probability from a dictionary of size L. And so my the number of words, the most likely next words, is just L at each position. I can't do any better than that. So ideally, when I see a particular word after a word history, I want my perplexity to be very small, right? Because remember, perplexity you need to relate to surprisal. So I need to be very, I shouldn't be surprised at all to have seen a particular test word after seeing a word history. This is the worst perplexity, L, which means that my model is not doing anything better than just a random model, which is just picking words uniformly at random from a dictionary of size L. Okay, so this is the highest perplexity that could be assigned by the naivest of models. Okay, so my model can only do better than this. And so this kind of motivates why the normalization makes sense. Okay, so the intuition for perplexity kind of very nicely given in Shannon's paper on language. So Shannon formulates what is known as this guessing game, okay, which is, can I predict what is the next character or next token or next word in a particular sequence? So what is the surprisal factor in predicting the next word? So say that my word history was at the Badlu stall, I had tea and then if you look at kind of all possible words that could fill this blank, you'll see that some words are, you know, much more probable, say biscuit, samosa, but some words are less probable and some words are extremely improbable, right? So a language model, a good language model, would assign a high probability to the actual word that fills the blank. Okay, and this correlates with lesser surprisal, right? Because I'm not surprised at all to see the word that filled the blank. Okay, if my language model was very good. And so lesser surprisal is essentially perplexity. So perplexity completely correlates with the surprisal factor. Okay, so higher probabilities assigned to the actual words would equate to lower perplexities. Okay, so now how does perplexity answer the second question that we had posed, which is how closely does the model approximate the actual test set distribution? Okay, so for this, we'll look at this particular divergence measure, which is called the Kullback-Leibler divergence. It's a measure which is used to compute the distance between two probability distributions. So here denoted by X and Y. Okay. So you can think of KL divergence, typically KL divergence between X and Y is when X is your true distribution, okay, which you don't really know, and Y is the distribution according to your model. So Y is the supposed to be the approximation of X. Okay, and then you're trying to find the distance between these two distributions. So KL divergence sometimes also referred to as the relative entropy. Okay, so it's the relative entropy from Y to X. Okay. You can also think of KL divergence as the information gain if one uses X instead of Y. Okay. And so in other words, you can think of this as the amount of information you're losing when you use Y to approximate X. Okay, so X is kind of your true distribution and Y is the model distribution. And KL divergence is asymmetric. Okay, it's so KL divergence of X, the relative entropy from Y to X is not the same as the relative entropy from X to Y. And this is how KL divergence is defined. Okay, this is the formula for KL divergence. And what this means is that the KL divergence between X and Y is zero if and only if these probability distributions are identical. Otherwise, KL divergence is guaranteed to be a non-negative quantity. So it's either zero or it's a positive value, okay, because of the way it's defined. Now, how do you measure KL divergence? Because you don't know the true distribution. So in our case, the true distribution is the true distribution over your words, okay, and Y is the distribution assigned to assigned by your language model, okay, to the to your words, to the words. So we don't know X. Let's rewrite the KL divergence measure as the cross entropy between X and Y, which is defined by this first term, minus the entropy of x. Okay, so here only the first term which deals with both x and y, right? Once you fix x, the second term is going to be the same. So let's now only focus on this first term, which is the cross entropy between x and y. Again, we don't know x, we don't know this distribution x, the true distribution. So you can imagine approximating this distribution, the cross entropy between x and y, with this empirical cross entropy. Okay, and so here, instead of, you don't have this probability assigned. So here sigma denotes a sentence, okay, in your test set. We don't know the probability assigned to sigma by x. Okay, so we're just going to replace that by 1 by the size of test. Okay, and here you're going to sum over all the sigmas in your test set and only look at the log 1 by probability of sigma assigned by your model distribution, which is y. Okay, so here's the empirical cross entropy measure. So 1 by size of test set is just the number of sentences in your test set. You need to further normalize this ECE measure, okay, by the average length. Okay, so that would amount to adding an additional 1 by the number of words divided by the number of sentences. Okay, and this just works out to 1 by n, where n is the number of words. Okay, so this is your kind of final expression of the normalized empirical cross entropy. And how does this relate to perplexity? So if you take the log of perplexity, so recall what was perplexity? It was 1 by the probability of the test, this entire thing to the power 1 by n, right? So if you take the log of that expression, you end up with this particular formula. And this can be further expanded by taking the product over every sigma in your test set. Okay, and then that just becomes summation over all sigma log 1 by probability of sigma as assigned by your language model. So perplexity is nothing but e raised to normalized cross entropy, because here this is your normalized cross entropy, empirical cross entropy measure, quantity. So perplexity would be e raised to normalized cross entropy. Okay, so commonly perplexity, the log is to the base of 2. Okay, so instead of exp, it's usually 2 raised to normalized cross entropy, empirical cross entropy. And because it's the base 2, perplexity is also referred to as, the quantity perplexity is also referred to as the number of bits. Okay, so here are some example perplexities for Ngram models. So you can see that as you go from a unigram to a bigram to a trigram model, the perplexity is kind of very quickly reducing. So there's a large drop going from unigram to bigram models, and then the drop is more gradual, right? But the lower the perplexity, the better your Ngram model. Okay, so that was about evaluating language models. I want to give you a very quick intro to LM smoothing, which was the problem we briefly discussed of unseen Ngrams being assigned 0 probabilities just because they don't appear in the corpus. So this was our example specifically, and we had this issue of never having seen the bigram dog eats, right? So even with having very, very large text corpora, as I mentioned, this is a very frequent phenomenon that you will run into these unseen Ngrams. Okay, and what is the kind of problem with maximum likelihood estimates, which is exactly what we used for the previous example? It maximizes the likelihood of the observed data, right? And it automatically assumes that anything unseen doesn't happen, right? So there is this danger of overfitting to the training data. And so here, smoothing techniques come to our rescue. Okay, and the basic philosophy of smoothing methods is that you're going to reserve some of the probability mass away from your seen Ngrams to the unseen Ngrams that you do not see in your training corpus. Okay, and then the way in which you can do this and implement these smoothing techniques, there are a variety of them. Okay, and so we'll first start kind of with the simplest of smoothing techniques, which is the add one smoothing technique or the Laplace smoothing technique. And the idea is just the following, which is that you add 1 to all bigram counts. Okay, so what would this mean? That earlier, if you had your bigram probability to be as follows, now with Laplace smoothing, you're going to add 1 to all bigram counts, which means, of course, you need to add plus v to the denominator, where v is the complete vocabulary size. Okay, so here, what is the kind of effect it has? Here's an example of bigram counts. So here you can, bigram counts are, this is the word history, and then this is the word which follows. Okay, so this is the count of I want, this is the count of want to, this is the count of to eat, and so on. Okay, so this table is from the chapter from Jurafsky and Martin, which is your assigned required reading for these lectures on language models. So these are the counts without any smoothing. So immediately see that this is fairly sparse. There are lots of zeros in this particular table. Now the whole objective of smoothing is that we want to remove these zeros, right? So here's the effect that add one smoothing has. All these zeros now become ones, right? And there is one added to all the scene engrams as well, to the count of the scene engrams. Okay, and here are the corresponding bigram probabilities. So earlier you had all these zero probabilities. Now you can see that those zero probabilities have become some small non-zero probability. Okay, but I want to alert you to something that has happened here, which is that these scene engram probabilities, which were fairly high, now you can see there is a substantial drop in the probabilities going from the not smooth case to the add one smooth case. Okay, and this is a problem. So all smoothing methods, like I mentioned, it is stealing from the rich and giving to the poor, right? Except here, you're stealing a little too much from the rich. Okay, so these are already MLE estimates of frequently appearing scene engrams. Okay, you don't want to take away too much from these MLE estimates, which are already quite reliable, okay, because there were fairly large amounts of counts of these scene engrams. But as a result of add-one smoothing, especially when you have a large vocabulary, what ends up happening is that you will be taking away too much from the scene engrams. Okay, so that's one problem, one immediate problem with doing something like add-one smoothing. The other problem is that the way in which you are distributing this probability mass that you have removed away from the seen engrams across the unseen engrams, it's exactly the same, right? You're not making any, you're not distinguishing between how you are going to distribute the probability mass that you have taken away from the seen engrams across the unseen engrams. You're going to do it in exactly the same way. Okay, that also may not be a very good strategy. And this is what we will kind of examine in much more detail in the next module. Smoothing techniques, which actually distinguish between how this probability that you have moved away from the seen engrams is going to be redistributed across the unseen engrams. So add-one smoothing has these issues. And so here the immediate problem which appears to be happening is that you are adding too much, like adding one to all these kind of unseen engrams appears to be too generous. Okay, so it's moving too much probability mass away from the seen engrams. So there's this very simple fix, which is referred to as add alpha smoothing, which is that don't add one to each count, but you add a small alpha to each count, where alpha is less than one. So then alpha is now this hyperparameter. So how do you choose alpha? This is a typical hyperparameter style. You choose a value that minimizes cross entropy on some held out set. Okay, so you try different values of alpha and then choose the kind of best value of alpha as determined by looking at the perplexities on a development set. Okay, so smoothing you can also alternatively view as discounting. Okay, so what do you mean by that? You can write the probability of a bigram with Laplace smoothing as, again, just like, so recall, this looks like the, this looks exactly like how you had defined the MLE probability of the bigram Wi minus 1 Wi, right? So here in the numerator, note that instead of the actual count of having seen this particular bigram, I'm going to use this discounted count. Okay, and the discounted count can be defined as follows. Okay, so here, um, this is another way in which you can view smoothing. And so what this would mean is you have these bigram adjusted counts. Okay, so you change the actual counts of your seen and unseen engrams. Okay, so this was kind of the most basic of smoothing schemes. I'll be discussing more sophisticated smoothing schemes in the next lecture. Okay. Now, before we wrap this session up, let me spend a few minutes talking about how Ngram models can be represented as weighted finite state acceptors. So now you know what an Ngram model is. Now, with no optimizations whatsoever, you can think of an Ngram model over a vocabulary of V words um, as being a weighted finite state acceptor, which has V raised to n minus 1 states and V raised to n edges. Okay, so here's a simple illustrative example. Say that I'm considering building a trigram model and I'm working with a two-word vocabulary A and B. Okay, so that immediately means, so it's a trigram model. So I'm going to look at bigram histories. So I'll have 4 of them, right? So AA, AB, BA, and BB. Okay. And what are all the transitions? So I'm going to have, so this is, remember, this is an acceptor. Okay, so here the symbol says B, and the corresponding weight is going to be the probability, the trigram probability of B given the history, which is A, right? And now my new history is AB. Yeah, so similarly, you will have another transition, which is B, the symbol B, and the probability of B given AB. So now you have A, so the probability of A given BB, and A, symbol A, probability of A given BA, right? And you'll also have self loops on AA and BB. So here you can see A stay in this state, and so it's just the probability of A given A. And here similarly you'll have B, and it's the probability of B given BB. Okay, and you'll have this additional 2 states. So you'll have a state going from here to here on B, right, is the probability of B given BA. Similarly, you'll have transition from here to here on A. So it's the probability of A given AB, right? So overall, there are 8 transitions, and there are 4 states representing your bigram histories. Okay, so I hope this structure of the finite state machine representing an Ngram model is clear. But clearly this is not at all practical, right? Especially when you have large vocabularies. The order of your Ngram is not typically going to be larger than a trigram. Okay, so N is, very likely going to be 3 at most. But V can be very large. Right? V can run into the millions. So this is clearly not a very practical structure. And so there is a modification when we talk about back-off language models. So we'll define back-off language models in the next lecture, and then we'll revisit the structure, the WFSA structure for Ngram models, specifically back-off models, and we'll talk about the modification that can be made to make these structures a little more compact.